Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.12. The problem statement says, aqueous solutions of the amino acid L-isoleucine, or IL, as I'll say in this problem, are prepared by putting 100 grams of pure water into each of 6 flasks and adding different, precisely weighed quantities of IL to each flask. The densities of the solutions at 50 degrees Celsius, plus or minus 0.05 degrees, are then measured with a precision densiometer with the following results. They give us a table of values. So they give us these table of values. And then part A says, plot a calibration curve showing the mass ratio, R, as a function of solution density, rho, and fit a straight line to the data to obtain an equation of the form R equals A rho plus B. We did this a lot in the last chapter, so you should be pretty familiar with how to do this. So part A, we have our equation, R equals A rho plus B. So A is the slope and B is the intercept. Okay. And we can solve this on the computer pretty quickly just by using the built-in functions of a spreadsheet. So if we put all these values into a spreadsheet, we can do a linear regression and just with the built-in functions and calculate that A equals 554.5 and B equals 0.0. Okay. I'm not going to show that how to do that on the computer, but how you would do it is the whole process is shown in my previous video. Any of the videos from last chapter, starting from about 2.33 onward, all use linear regression. So you can just go back to one of those videos, watch that first part of the video where we do a linear regression, solve for a slope and an intercept, and you should be good to go. So I won't show that part here, but that's the answer to part A. Okay, so for part B, the volumetric flow rate of an aqueous ILE solution at a temperature of 50 degrees Celsius is 150 liters per hour. The density of a sample of the stream is measured at 50 degrees Celsius and found to be 0.994 grams per centimeter cubed. Use the calibration equation to estimate the mass flow rate of ILE in the stream in kilograms ILE per hour. So we know that the volumetric flow rate of the solution is equal to 150 liters per hour. We want to, they also give us the density, which is equal to 0.9940 grams per centimeter cubed. And what we want to know is the mass flow rate of ILE. Okay. Let's start writing down some of the things that we know about this. We know that the mass flow rate equals the volumetric flow rate times the density. And so we can get the mass flow rate of the stream. And that equals... Then we know that the mass flow rate of the stream is equal to the mass flow rate of ILE plus the mass flow rate of water. And we know what R is in terms of grams of ILE per 100 grams of water. So if I had 100 grams of water, I would have R grams of ILE. Okay. So we want our equation here to have something that looks like grams of ILE per grams of water. So let's divide this equation by the mass flow rate of the water. Okay. Now we know that this term here needs to be per 100 grams of water in order to be R. So let's turn this into R. Okay, so how we relate this term to R, we take a look at R and we know that for every 100 grams of water, there's a small amount of grams of ILE. So we know that most of the stream is going to be water. Okay, so let's keep that in mind. So if you end up doing your unit conversion wrong between grams of ILE per 100 grams of water, if you end up doing your unit conversion wrong and you find that you have way more ILE than you have water, you know you did something wrong and you need to go back and make a correction to how you did this unit conversion here. So we know that R is 100 times bigger than what this ratio is. They have the amount of ILE per 100 grams of water, so we know that that R is 100 times bigger than it would be if you just had the ratio by themselves. So if we divide R by 100, we'll get this ratio. Okay. Having the units written in that way can be a little confusing, but hopefully it made sense that, you know, if you have 100 grams of water, you have a small amount of ILE, and so they're getting 100 grams instead of just 1 gram of ILE, then that R number would be a lot smaller. So you can think, oh, I need to divide R by 100 to make that a lot smaller, because we're doing this on a per gram basis instead of on a per 100 gram basis. So we're reducing that number. Okay, so R is divided by 100. Okay, so now we have this number here. If you take a closer look at this, you can see that that's just the mass fraction, the inverse of the mass fraction of water. So you have a certain amount of water in the stream, and then you have the total flow of the stream, and we have the reciprocal of that. So let's take the reciprocal of this so we can work in the mass fraction of water. Okay, so now we've found out what the mass fraction of water is. That's great. So now we can use our other relations like H2O plus ILE equals 1, or we can use this function. We could use a mass balance here and figure out what the appropriate values and calculate what the mass flow rate of ILE is. So I'm going to go this route. Okay. Now all we have to do is plug in our numbers here and make sure we do our unit conversions correctly. In order to calculate what R is in this example, we have our function R equals A density plus B. They gave us the density right here, so we would use the solution density that they gave us and the parameters that we solved for in part A, and that correlates to an R value of 3.196, and then we put our R value into our mass fraction function and calculate the mass fraction of water, and then we know what the total mass flow rate is. We calculated that here, and we know the mass fraction from this function, so then we calculate what the mass flow rate of water is, and we do calculate the total mass flow rate of ILE, and then this should equal 4.6174 kilograms per hour of ILE. Okay, so that's the answer to part B. Okay, so for part C, this is a qualitative question. It has been discovered that the thermocouple used to measure the stream temperature was poorly calibrated, and the temperature was actually 47 degrees Celsius. Would the ILE mass flow rate calculated in part B be too high or too low? State any assumption you make and briefly explain your reasoning. Okay, so we're saying that the actual temperature, is low. So that means the actual density is high. The actual density is higher just from the temperature change, not from ILE. So that would then make our perceived R concentration increase. We would accidentally calculate a higher R, which would mean that we have a not real increase in mass flow rate of ILE. The density increase wouldn't be due to a higher concentration in ILE, but we would perceive such because the temperature was lower. And so the perceived amount of ILE would be higher, when in reality the real mass flow rate of ILE would be lower. So would the ILE mass flow rate calculated in part B be too high or too low? It would be too high. In part B, we'd calculate a certain amount of ILE flow rate, assuming that the temperature was correct, but that density was not caused by a higher ILE. It was caused by the lower temperature. So our real ILE flow rate is lower. So our calculated ILE flow rate is too high. Hopefully I said that well enough so that you can distinguish between the two there. Okay. So the assumption that we made is that when the temperature decreases, the density of the solution increases. That's the assumption that we made. That's not always the case, but it is the general rule. For water, for a stream that is mostly water, and it's at 50 degrees Celsius, water's density does follow that rule. I don't know exactly how it behaves as a solution, but because it's nearly all water, I think it's a pretty safe bet to say that when the temperature decreases, the density also increases. Well, that is it for problem number 3.12. Thanks for joining me. If you have any comments or questions about this problem, let me know in the comments below, and I will get back to you and try and make a discussion out of it. Thanks for joining me, and I hope to see you in the next video. Thanks, bye.